Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier analysis and in particular the Fourier series of a continuous time periodic function. Alright. So, in this module let us start by looking at the conditions for the existence of the Fourier series. Okay. So, what we want to start with is the conditions for existence of Fourier series. Under what conditions does the Fourier series converge? Okay, conditions for existence of the Fourier series. So, basically known as the conditions for the convergence, okay, for the Fourier series to converge. That is conditions for the Fourier series to converge, and these are also known as the Dirichlet conditions. These are also known as the Dirichlet, after the mathematician Dirichlet. Okay, so these are known as the Dirichlet conditions. Okay. So, x t has a Fourier series representation, that is the periodic signal x t has a Fourier series representation if it satisfies the Dirichlet conditions, if it satisfies the Dirichlet conditions, and these are as follows, that is the Dirichlet conditions which are to be satisfied for the existence of the Fourier series are as follows, that is x t is absolutely integrable over a period. This implies, that is, if you look at this integral over a period of magnitude of x t dt, this has to converge, or this has to be a finite quantity. So, over a period, if you integrate magnitude of x t, that is integral over any period t of duration t naught, contiguous period of duration t naught, where t naught is a fundamental period, correct, integral over any fundamental period t naught, magnitude x t dt has to be a finite quantity. Okay. So, this has to be a finite quantity, and 2, x t has a finite number of maxima or minima. So, the other condition is x t has a finite number of maxima or minima, finite number of maxima in any finite interval, in any finite number of maxima or minima in any finite interval over time. in any finite interval over t. And the third condition, that is the number of, that is if you look at any interval of a finite duration, the number of maxima and minima, that is the number of extrema of this signal x t has to be finite. Okay. And the third condition is that x t has a finite number of discontinuities, the signal x t has a finite number of discontinuities. X t has a finite number of discontinuities within any finite interval of duration t, any finite interval. Over t, and each of these discontinuities is finite, and moreover that it has a finite number of discontinuities. Okay, it has a finite number of discontinuities, and each of these discontinuities is finite. Okay, that is the third Dirichlet condition. So, these are the three Dirichlet conditions. Dirichlet conditions, that is, your first is that x t is absolutely integrable, that is integral over any fundamental period d naught of the magnitude of x t has to be finite, all right, and x t has a finite number of maxima or minima in any finite interval of finite duration over time, and finally x t has a finite number of discontinuities, and at each of these points the signal x t is finite in any interval of finite duration over time. Okay. Now, an important thing to note is that these are sufficient conditions, right, these are not necessary. Note the above Dirichlet conditions are sufficient these are sufficient but not necessary. Okay. Implies that the Fourier series exists if the Dirichlet conditions are satisfied, but not the other way around, that is it is not that the Dirichlet conditions are satisfied if the Fourier series exists. Okay. So, these are sufficient conditions, all right, which means that if these conditions are satisfied by the signal x t, then by a periodic signal x t, by a continuous periodic signal x t, then the Fourier series exists, all right. So, these are in summary, these are the conditions for the Fourier series to exist for a continuous periodic signal x t. Okay. All right. Let us also look at the next topic, which is the amplitude and phase spectrum. So, what we want to look at now is the amplitude and phase spectrum of this continuous periodic signal, amplitude and phase spectrum of x t, where remember we are still looking at a continuous periodic signal. they are looking at a continuous periodic signal. Now, the complex Fourier series coefficients of x t, remember these are complex, the complex of x t can be expressed as magnitude, this can be expressed as C k equals magnitude C k e raised to j phi k, okay. That is, this is the magnitude of C k and this is the phase of C k. This is the phase. In fact, you can also write phi k equals the angle of this coefficient C k. Okay. Now, plot, if you plot this magnitude C k versus the frequencies, the discrete frequencies, that is k omega naught. Remember, the coefficient C k are defined for the fundamental frequency omega naught and multiples of the fundamental frequency, that is at harmonics corresponding to omega naught. So, if you plot this magnitudes of the Fourier coefficient C k versus k omega naught, all right, versus omega, this is termed as the magnitude spectrum of the signal x t. Okay. So, plot of the magnitude C k versus angular frequency omega, correct, angular frequency omega, this is termed as the amplitude spectrum. This is termed as the amplitude spectrum, and similarly plot of phi k, that is which is the angle of C k versus omega, this is termed as your phase spectrum. Okay. The plot of phi k versus omega, that is the phase versus omega, this is termed as the phase spectrum. Now, observe that these only exist, that is this magnitude C k and phi k only exist at discrete set of points, that is at k times omega naught, where omega naught is the fundamental angular frequency. Therefore, this is also known as a discrete frequency spectrum or also known as a line spectrum. Okay. So, note, okay. So, note that C k, so note that magnitude C k comma phi k, these are not continuous functions of omega. Of the angular frequency omega. Okay. These exist only at discrete set of frequencies. K omega naught, where k is an integer, and omega naught equals fundamental angular frequency. Okay. These only exist at a discrete set of frequencies and therefore, hence termed as the discrete frequency spectra or line spectra, hence termed as a discrete discrete frequency spectrum, or what is also known as a line spectrum. Discrete frequency spectrum or a line spectrum. Now, further, if you look at a real periodic signal, when the signal is real, remember we have said that the Fourier coefficients, right, the Fourier coefficients, that is C of minus k, is the conjugate of the Fourier coefficient C of k, corresponding to k of corresponding to the frequency k omega naught. So, for a real signal, in fact, for a real periodic signal, x t, we have the coefficient C of minus k equals C k conjugate. Now, what this means is, this implies, now firstly this implies that magnitude C of minus k equals magnitude, because they are complex conjugate of each other, magnitude C of minus k equals magnitude C of minus C of k, implies the magnitude spectrum is an even function of frequency. Okay. Magnitude spectrum is an even function of omega. Further, we have, since they are complex conjugate of each other, this also implies, what this also implies is that the phase or angle of C of minus k, phase of minus k is minus of phase of k. This implies that the phase spectrum is an odd function. So, we have magnitude spectrum which is an even function, the phase spectrum which is an odd function. This is for a real periodic signal x t. Okay. All right. Let us now look at the power of this periodic signal and the property of the power. So, let us now look at another aspect, that is the power of the let us now look at this other aspect, which is the power of the periodic signal, and we have power of the periodic signal this is equal to, this is given as p equals 1 over t naught. This is defined as integral 1 over t naught over any fundamental period t naught magnitude x t square dt. This is the power of the periodic signal x t. Now, what we are going to do is, we are going to prove a property using the Fourier series. So, consider the Fourier series of x t Now, consider the Fourier series of x t given as x t equals summation k equal to minus infinity to infinity C k e raised to j k omega naught t. Let us say this is the Fourier series. Then magnitude of x t square is, remember, magnitude of a quantity square is simply x t times x t conjugate, okay, which is equal to, now first I am going to write x t, which is, we already have the expression in terms of the Fourier series, that is summation over k C k e raised to j k omega naught t multiplied by x t conjugate, I am just going to change the index, that is summation m equal to, and I can change the index, summation m equal to minus infinity to infinity c of m e raised to j m omega naught t whole conjugate. And now, if I open the brackets and expand this, what I am going to have is I am going to have summation k equal to minus infinity to infinity, summation m equal to minus infinity to infinity c k c m conjugate times e raised to j k minus m omega naught t. Okay. So, this is what I have. So, what I am doing is basically I am representing x t in terms of its Fourier series, considering x t into x conjugate of t, okay, and that gives me magnitude x t square. Okay. And now, therefore, for the power, for the power we have 1 over T naught magnitude x t square dt, this is 1 over T naught, substitute the expression above for magnitude x t square, this is 1 over T naught, that is integral, remember this integral is over any duration T naught, any period or any time interval, contiguous time interval of duration T naught, summation m equals minus infinity to infinity c k c m conjugate times e raised to j k minus m omega naught t dt. And now, if I integrate, now if I interchange the sum slash integral, we bring the summations outside. So, that will give me k equals minus infinity to infinity summation m equal to minus infinity to infinity c k c m conjugate 1 over T naught integral over duration T naught e raised to j k minus m omega naught t t, and we have seen this integral, that is integral of any harmonic of omega naught, right, any complex exponential with its frequency that is an integer multiple of omega naught, you integrate it over the period T naught, it is 0 unless, alright, unless k is equal to m, in which case this is e raised to 0, which is 1, the integral over duration of T naught is T naught divided by T naught, which is 1. So, this is equal to 1 if k equals m and 0 otherwise, implies this is basically the discrete impulse, that is delta k minus m equals 1 if k equals m, k equals to m and 0 otherwise. So, this is summation k equals minus infinity to infinity summation m equals minus infinity to infinity c k c m conjugate delta k minus m, which is of course now exists only, that is now only the terms corresponding to k equal to m survive, all the rest of the terms are 0. So, this is summation k equal to minus infinity c k into c k conjugate, which is magnitude c k square. And therefore, we have showed a very important property, a very important and very interesting property, which is basically that if I compute the power in the time domain of this periodic signal, that is magnitude x t square dt, that is equal to summation k equal to minus infinity to infinity magnitude c k square, and this is known as the Parseval's identity or the Parseval's theorem. So, this important property is known as the Parseval's identity or this is also known as Parseval's theorem. Okay. All right. So, that is an interesting property. So, what we have seen in this module is we have looked at the conditions for that is the Dirichlet conditions for the existence of, which are the sufficient conditions for the existence of the Fourier series representation or the convergence of the Fourier series representation of a periodic signal, continuous time periodic signal x t, and we have also seen the Parseval's relation which relates the power of continuous time periodic signal x t to its Fourier series representation. All right. So, we will stop here and look at other aspects in the subsequent modules. Thank you very much.